In this lesson, we're going to learn about objective 3.12, the photoelectric effect. So this learning objective states that we should be able to explain the properties of an absorbed or emitted photon in relationship to an electronic transition in an atom or molecule. So let's first start talking about the photoelectric effect itself. So this is the observation that many metals are going to emit electrons when light shines upon them. So this light that shines upon it is actually considered a photon. So a photon is actually a carrier of energy coming from that light. I do want to note that a photon is massless, so has no mass, and doesn't have a charge. This gets mistaken a lot because people like to think photons mean electrons, or they think that they're negative. No, photons have no mass and they have no charge, okay? Actually, according to Einstein's theory about the photon is actually responsible for transferring the energy needed to eject these electrons in the photoelectric effect. And so this amount of energy that the photon brings must be high enough. What that's saying, it needs to have sufficient energy to actually emit that electron, to eject that electron from the metal. So if this photon is hitting the metal and nothing is happening, that means that the photon doesn't have enough energy. And so we're going to actually talk about, well, how do we figure out how much energy it has? And it has something to do with frequency and wavelength when we think about the ER spectrum, okay? So when a photon is absorbed by an atom or molecule, this also can be vice versa, from absorb to released. Here, the energy of the species is increased by an amount equal to the energy of the photon. So we can say that the energy of a photon, which by the way, energy will be in joules, J, the energy of a photon will be directly proportional to its frequency, which will be denoted like this, and inversely proportional to its wavelength. Wavelength will look like this. So the wavelength of the electromagnetic wave is related to its frequency and speed of light by this equation. So from your equation sheet, you will see this equation. Here, C is going to be, I'm going to zoom in just a little bit. C is the speed of light. This is going to be a constant. Some resources actually say speed of light is 3.0 times 10 to the 8th. AP Chem wants you to have it as 2.998 times 10 to the 8 meters per second. I know it's not that much of a difference, but I would use whatever value is given to you. And like we had mentioned, wavelength is there times the frequency, okay? Next, the energy of a photon is related to its frequency of the electromagnetic wave through Planck's equation. So here, energy, E, is H times V. So this H is talking about Planck's constant. So like C is a constant, H will also be a constant. This is 6.626 times 10 to the negative 34 joules times second. So taking Planck's constant, multiply by the frequency, we should get energy, okay? All right, moving on, we actually can combine both of these equations because there's going to be times where you're given a wavelength and you're trying to figure out how much energy that is. So here, taking this equation in this one, let's say we were only told wavelength and we didn't know the frequency. Well, you will notice frequency is a variable in both equations. So if I rearrange this one to get to get frequency by itself, I get C over wavelength. This, thankfully enough, can be plugged into our energy equals Planck's constant times frequency to make us a new equation, E equals hc divided by wavelength. This is not on your equation sheet, but you should be able to rearrange that equation. How I memorize it is that the H and C are the only constants in these two reactions. So the constants go on top and the wavelength goes on bottom. Again, do what you need to do to help memorize that. All right. Overall message, electrons are ejected when light hits metal only if the frequency is high enough. Okay, so let's look at this picture. So you can see here are these photons, these carriers of energy hitting this metal. The metal has its electrons in that sea of electrons. And if the photon's energy is enough, boink, we have an emitted electron because it got enough energy from that photon. And then when we look over here, I'm going to zoom in just a little bit. So here at the bottom, it actually says that it tells us that potassium requires 2 eV to eject an electron. So looking at all three of these photons, the red one only reaches 1.77 eV rather than that required 2. So here, no electrons are going to be emitted because there was not enough energy. And there wasn't enough energy because look at the wavelength. The wavelength was at 700 nanometers. Okay, the higher the wavelength, the lower the frequency. And then here, looking at the green, it will end up actually giving us, dropping down that wavelength, we increase the frequency. So here we get 2.25 eV. So here we were able to get enough of that electron emitted. And then in the last one, we have an even lower wavelength. We got definitely more EV. We have 3.1. Here you can actually see that it ends up going further compared to the green one. Okay, so here, knowing that relationship between wavelength and frequency, they are inversed, and then frequency to energy directly related. Okay. All right. Few quick things to just like go over. It is very useful to know that wavelength is measured in nanometers. Nanometers is going to be nm, okay? On your equation sheet, which it used to not be like this, they actually tell you the nanometers to meters conversion. It should be fairly straightforward to memorize though. Nano kind of sounds like 9. So here the conversion is 1 times 10 to the negative 9 meters equals 1 nanometer. All right? Here, let's kind of look at the ER spectrum right here. You can see here, this is increasing in wavelength while energy is increasing this way. And so mostly what we are working on is visible light right here. So that's talking about those wavelengths, the blue, the green, yellow, red. And so this gets related to Beer-Lambert's law, which you should have learned in Unit 1. It technically would be the objective after this objective, 3.12. Here, visible light is what we see. So whenever we see a blue, that's not blue. Whenever we see a blue solution, that's just what we see. If we talk about the blue solution absorbing stuff, that's actually going to be at a different wavelength. It's actually going to be opposite, and that is just something referencing the color wheel. So it would be somewhere around the red-orange. But again, that's going to be objective 3.13, the Beer-Lambert's law. All right, let's do problem 1 together just to try some calculations. So here, what is the energy? So we're solving for energy in joules with a wavelength of 575 nanometers. So remember, we know these two equations from our equation sheet and from the beginning of our notes. We are solving for energy, but we were only given wavelength. Seeing the equation wavelength is in, I would need to know frequency, which I do not. So here I can rearrange this, remember, to make E equals the two consonants on top. divided by wavelength. Now, before I start plugging things in, remember that c, our speed of light, is in meters per second. We were given nanometers for our wavelength, so we need to convert nanometers to meters first. Here I get 5.75 times 10 to the negative 7 meters. Now I can use hc over wavelength to plug stuff in. Again, h and c are constants that are on your equation sheet. My advice, be very careful punching this into your calculator. You don't want to mess up anything. Energy is going to be 3.45 times 10 to the negative 19 joules. That will be our final answer with 3 sig figs coming from the 5, 7, and 5. All right, I have a quick problem 2 for you to try. So why don't you pause the video, try this out yourself, then click play, and I'll go over the answers. So in this one, we had to calculate the wavelength in nanometers, as well as solve for the energy of light that has a frequency of this. So here, actually, this is kind of like a two-part problem. Here, it doesn't matter which part you start with. I ended up starting with the energy one. So here, E equals Planck's constant times frequency. I just multiplied those two values together. I ended up getting the joules as 9.9 times 10 to the negative 19 joules. In the second part, we're going to use speed of light equals wavelength times frequency. I ended up rearranging it to get wavelength by itself, so c over frequency. I divided speed of light by that frequency, and I got 2.0 times 10 to the 7 meters, but we're not done. We need to convert to nanometers. I ended up getting 200 nanometers. Now, if you really wanted to be on with the sig figs, you would make it 2.0 times 10 to the second. My advice is they probably would never put a problem like that because we generally see wavelength as a whole number that has 3 numbers, that 2, 0, and 0. So that would be the type of answer you would have. I wouldn't worry so much about sig figs when it came to the nanometers.